So tell me a little bit about where you're at and what you're up to.
So about my background, I am a physicist by academy. Then I did a PhD in quantum computing in the early age of quantum computing, in the sense of starting to do research like 10 years, 12 years ago. And now I work in a company doing quantum random number generators for post-quantum cybersecurity, both for quantum key distribution and post-quantum applications.
That's amazing. And I'm
Yes.
super interested. Quantum is a very interesting field to me. And one thing that my cybersecurity expert I work with, he explicitly tells me to use an application called Polynom. I don't know if you've
Mhm.
heard of that.
No.
So it's supposed to have post-quantum
Mhm.
cybersecurity-based technology. This geochain we're working with is also supposed to have that because the way it operates is nonlinear operational dynamics. Now, I know quantum computing is far different than people even understand. They're like, oh, it's fast. I'm like, it's not. eh. But
No,
I want
it's
to
not
hear from the
that.
expert.
Yeah.
What do you want to share with me? Like, oh my God, I have questions, but you go.
So I can share both in cybersecurity with quantum relationships there as well from quantum computing as well, and why enter in the field of quantum computing and then move to quantum round numbers or quantum cybersecurity.
That'd be great.
So yeah, so this goes all the way back when I was doing my degree in physics. I was doing computational physics and the hydrogen molecule. So you have two protons and two electrons there. And I was doing a Monte Carlo method to find the ground state of that molecule. And by that time, quantum computing was not even existing like the term. So people didn't even know that it started to be a thing. Like, I mean, the 80s, people in the field, like Feynman started the quantum computing, but like not many physicists knew about it. And then I started reading about quantum computing and say, so you're telling me that all the complexity I'm doing with this super simple molecule will be much simpler to do with a quantum computer because basically quantum computer will simulate quantum physics much easier. That's the whole purpose, right? So then I decided, okay, let me go into this field as a PhD because I am a quantum physicist. If I want to do quantum physics and I know that a quantum computer will exist, like all the things that I will be able to do in like 30 years, will be able to do in few years or even a month with a quantum computer. So I decided, okay, let's go into quantum computing. So I did my PhD at UCL in London in quantum computer. We will my supervisor at the time he created a theoretical concept of transport a quantum state using spin chains. And the idea was to be able to transfer quantum states from one place to another. So once you perform a quantum gate, you have a result from your quantum computer, and then you want to transfer to another place of your quantum computer and able to do the next operation or the next step. So because qubits cannot be at that time easily transferred from one place to another. So it's not like you can transfer information a computer and you just send a one or a zero. A qubit is way more complex, so you cannot easily transfer it. So the idea was to use spin chains. So you use the same uh, unit block of your qubit, and you have an array of them. And then by controlling the interaction between them, that you can transfer the qubit from a state from one place A to a place B, and then you're able to operate in a much bigger scale quantum computer. So the idea was like starting to build networks that right now are starting to be used in quantum computing or quantum networks to be able to scale because at the moment we don't have large qubit systems, but we will, in order to scale up, we need to use multiple quantum computers in a sense. So yeah, my work was then at the time was starting to do physical implementations of these spin chains. So the initial idea was to use carbon nanotubes with 360 molecules inside. So it's a fullerene carbon sphere in which you have 60 carbons, and inside of it you have a nitrogen. This nitrogen acts as the qubit, and then it will interact with another nitrogen that is in another sphere inside, and then you have a chain of these spheres, and that way you will be able to transfer the information inside these.
How many nanometers are these spheres in diameter?
We're talking about less than 50, 60 nanometers.
Perfect. Please continue.
Yes. So then I started to add temperature to the system. I started to add magnetic fields, and then the complexity started to grow so much that the simulations in a classical computer were not feasible. So we decided to move to quantum dots and start doing quantum gates with quantum dots. So the idea was to create entanglement electrons. So as you are aware, entanglement is one of the fundamental properties of quantum computing, and you able to generate entangled particles and distribute them in a quantum computer is fundamental for transferring data later on and teleport states from one place to another. Are you familiar with that, right?
I will have something I have to ask you later, but I do want you to continue.
Yes. So then basically we carry on a lot of research on quantum dots, and then I was approached by a university groups that was doing cold nanoparticles, and they're using quantum dots for temperature measurement. And the idea was to create a new treatment for cancer using gold nanoparticles. So you introduce these gold nanoparticles into the cancer tumor, and they will absorb radiation that is transferred to the human body, but only absorb in the frequency for these plasmons that are happening in the gold nanoparticle. And then we measure the temperature with the dilatation of the quantum dot. So the quantum dot will start to expand, and because it expands, then the energy levels on the quantum dot will shift, and then the frequency of emission of the quantum dot will be different. So you can use the frequency of emission of the quantum dot or absorption as your temperature and as your thermometer inside of the body that you're treating with the radiation. So that was quite interesting work that I did on plasmons and absorption of plasmons in my final time for my PhD.
Most people don't even know anything about what you're doing. They don't, wow, this is amazing.
Yes. I can go deeper if you want, or I can carry on with the background, and then we can go deeper in certain topics, as you wish.
Carry on a little bit more about your background, and then we'll dive in deeper.
Okay, good. Then basically, I went to Singapore after finishing my PhD, and the idea there was to work in quantum networks and try to do the group in Singapore had a theoretical model of a quantum network. The idea is that they will try to do a physical implementation of quantum network and then an application built on top of that. I was looking and I found a very interesting application that is the quantum version of the Google PageRank algorithm for ranking websites. And the quantum version of that is able to distinguish ranks between websites that the classical version of the algorithm is not able to do. So we, using the quantum version, then you're able to fine tune better the ranking of links in a network, basically. And the idea was to use optical cavities for the nodes of the network. So you will have different optical cavities as each of the nodes on the network, and then you connect them by fiber optic. And basically, with that, you will be able to map the network that you have in your, let's say, in a website network, and then you map that to these optical cavities and fiber optics, and then you will be able to rank by the presence of number of photons in the optical cavities. The larger the amount of photons, then the more important is that node in a network. And that is more or less the end of my academic life. And now I work in the industry in the quantum number generation. So this goes with at the beginning when I did the studies in quantum computing, you study like protocols for quantum key distribution in which you have to select bases and they tell you, you select bases at random and that's it. They don't tell you how you generate random numbers with quantum mechanics. I mean, you have concepts like quantum superposition where you measure, you have a random event and so on, but how do you actually physically produce a product that gives you quantum round numbers? And actually that's a challenge. It's not as easy as one can think of because a lot of the problems when you want to create product is actually economics. So you want to be able to put them in the market and you want to be able to people to be able to use them and not be a fancy experiment in the lab.
Yeah,
So
absolutely.
yeah. So we are at Crypto Labs at the company I'm currently on. We are one of the first companies that are producing quantum round numbers. We're able to miniaturize them. We're able to start scaling it. We have done a space-grade quantum random numbers for quantum key distributions in the space, for example. That was a very interesting project that we have done. So we are working now with companies that are looking to integrate quantum random numbers for quantum key distribution as well as post-quantum technologies.
So this is really neat because this really is the bleeding edge of technology that I would say the top 1% of the 1%, maybe even the 1% of that, are aware of, because quantum mechanics and the theories and ideas behind it and the applications are so counterintuitive to how people think reality operates. But as we've learned, that there are things that in this universe do not make sense intuitively, obviously. Do you mind if I ask you a question, or do you want to dive deeper?
No. Please, do a question.
So this will be so I'm going to tangent you for a little bit, but it is directly related to quantum mechanics.
Mhm.
Are you familiar with orchestrated objective reductionism?
No.
Okay, that's fine. So are you familiar with a man named Roger Penrose?
Yes.
Okay, so I'm going to walk you through this a little bit. Roger Penrose worked with an anesthesiologist, and he assumed off of observations during the administration of an anesthetic that the microtubules within the neurons of the human brain were acting as conduits in some way for a quantum interaction. And the way he postulated this was there are these non-computational Platonic mathematical truths, basically things we don't understand that are true outside of standard dimensionality. And originally he received a lot of criticism for this theory. And to help you understand it, they basically identified that when a person is conscious, these microtubules are vibrating. And just so you're aware, they're semi-symmetrical and they're between 1 and 23 nanometers in size. Now, I think 4 weeks ago now, there was a publication on a rodent study. And in that study, they identified a microtubule stabilizer, meaning something you could administer that would cause the tubules to stay vibrating even after you administered an anesthetic.
Okay.
And
so
then
when you're conscious, they're vibrating, and now you're on the aesthetic, and they put you this, and they're vibrating. Okay.
Correct. And then they took one group, they administered the stabilizer, and they administered the anesthetic. And then they took another group and they administered just the anesthetic. And what they found is the group with the stabilizer stayed conscious for a longer period of time than the group that received the anesthetic, showing evidence, because this, to conclude, essentially, they're in the current theory of reductionistic consciousness to the biomechanical brain. There is no answer to what this study illustrated. Now, I'm going to take a skip step here and talk to you about something I reviewed about 3 years ago and is now going through production. There was a group that was using a laser system. They had developed a laser system that would ablate a target alloy, and the target alloy would then, of course, release its material into a fluid. And then they had a cross-beam laser with a magnetic field that would cause the material to concisely form into nanospheres ranging between 1 and I believe 40 nanometers in size. Okay. Or roughly, I would say probably 40 to 100 nanometers, but within that range.
Okay.
And under an electron scanning microscope, high fidelity, they were able to identify that these were completely symmetrical spheres. And I've seen this. Now, what's interesting about this, and this is where it's going to draw your interest, is they took a standard, I would say roughly 1 foot tall antenna, low frequency RF antenna, standard power, I think about 0.2 milliwatts. And then they put it and encased it in about a foot thick of concrete. And they buried it not too far underground, like just maybe a foot or two. And then they turned it on to test its broadcasting range. And as you know, an antenna under standard conditions like that would not broadcast at all. And if it was outside of the box and not underground, you might get 6 kilometers, I would assume, something like that, maybe something like, yeah. Well, here's where it gets interesting for you. They picked up the signal, not just several hundred miles away or over several hundred kilometers, but they picked it over 1,000 kilometers or even actually over 1,000 miles away in this instance, because I know the conversions obviously are not correct. It's roughly, anyways, I don't want to go into that. But they picked it up really far away. When I read this paper, I was like, this isn't possible. And then they gave me a subsequent study where they'd taken the same situation of using these nanoparticles, and to tell you what they call them high energy allotropic alloy nanos or nanoparticles, nanospheres, along that lines. And they took it in a system. They took it out into the Gulf of Mexico, and they dropped it down into roughly 4,000 feet of water. And it successfully broadcast through that water back to the shoreline with a 0 loss of signal. And if I look at the exact numbers, the decibel ranges were very high. And as you know, that's a logarithmic curve.
Yes.
0 loss of transmission or fidelity of the signal. And this is also for the other study they did. I couldn't identify anything that I know of in quantum that could explain this, because as I know, information transfer of the entanglement, that's impossible. And you'd have to have 2 sides. So do you have any thoughts on how that could even work?
So when I was doing the Singapore project, I also was doing an application for a project that was in the antenna receptors in chloroplasts for photosynthesis in plants.
Yeah.
And the idea was that it's impossible to explain with classical physics the high fidelity of the transmission of around more than 99.6% of energy from the antenna receptor of the photons to the reaction center. So you have 8 chloroplasts doing a ring there, and you cannot explain with classical physics the high transmission quality. So it rings a bell there in that sense. So the only way to explain that high quality transmission from one antenna to another place is with quantum mechanics. And that's why they're applying for quantum biology in the photosynthesis process, quantum mechanics, to understand how much fidelity you have or no losses almost in the transmission of energy.
Yeah. It makes me, are you familiar with the blind man and the elephant? Have you ever heard that?
It rings a bell, yes.
So you have a blind man and you have him walk around an elephant, and he grabs the tail and he's like, this is a donkey. And then he walks and they take him to the front and they have him grab the trunk and he says, this is a snake. And I feel like that's kind of what we're looking at with quantum mechanics. For instance, the electromagnetic field is a component of a higher dimensional structure, and we're only touching at the baseline, because I don't know how to explain this thing, for instance, with the energy transfer in the chloroplasts and how that would work. Like, quantum is our best bet, but what is that?
in the sense of why quantum explain it or
How
why.
does quantum explain the energy transfer right now?
So, so basically, when you have a closed system, right, there is no interaction of energy with the outside. You have basically a perfect transfer of energy in a closed system. Only when you interact with the external world is when you can have losses of energy in an open system, right? So usually when you have states that are not interacting with the open world in a sense, they should operate with no losses. So that's also one of the reasons why you can only, or a lot of the things regarding superconducting also have quantum phenomena there. Because if once you have an open interaction, that's when you have start to have a lot of losses. Only with quantum closed systems is when you can operate with no losses in energy.
Okay. So I understand, okay, so we have a closed system.
Yeah.
Now, to a general audience, if we were to say a closed system, I don't want to put words in your mouth because that's not what we're here to do. I'm just trying to interpret this correctly. For instance, with the transfer of this energy, we're saying closed system. So it's not interacting with what we know to be our realm, our dimension. How would you even think that?
So basically, you have the chloroplast. You have the first interaction with the open system in the sense will be the absorption of photon from the antenna. Once that energy is absorbed, then you have now what we will call a closed system. That is, that energy has been absorbed by the antenna, and then you have the ring of chloroplast that will move that energy to the reaction center. So as long as there is no interaction with the external world of these 8 chloroplasts, then you have a closed quantum system in which there is no loss of energy. If there is interaction with the external world, then there can be losses like vibration. When molecules collide, the vibrations will move from one to another, and then there will be energy losses there, for example. But as long as there is no exchange of energy with external cells of this chloroplast, then you can keep the transfers need with no losses.
Okay. In this case, then, because these antennas, you had one that had these, what we'll call high energy nanospheres, that they're
Yeah.
theoretically assuming there's some type of resonator and that they're
Mhm.
resonating when they're hit with the output from the antenna. But what does that mean with the receiving antenna, where it's not coated with these particles?
No, as long as, so you have the two-step interaction. One is the receiving antenna absorbs energy, and once you have received that energy, you have a new system. That is the previous one with the extra level of energy, in a sense.
Mhm.
Now you close that system, and as long as that system does not interact with the external world, it can keep the same amount of energy ad infinitum in time, in a sense.
My brain's
What
breaking at how that's a closed system.
that's why it was very interesting to find that phenomena in plants, because finding quantum phenomena working at non-zero temperature is astonishing. Because
Yeah.
it's like how is it possible that you can keep that amount of energy if you're in theory with temperature, and temperature means collision of molecules one with each other. So that's under study. So this is one of the two phenomena that we know in biology that can only be explained with quantum mechanics.
What's the other phenomena?
Is how birds are able to positionate themselves with the magnetic field of the planet in order to do migrations. So how they orientate the birds, they use entanglement in their brain, and that's how they're able to measure the magnetic field of the planet. And then by knowing the measurements that they have, they know in which orientation they need to navigate the birds.
Do we have we identified where they're receiving that information in the brain? Is it within the neurons or?
And I am not on,
I'm
I
going to look it up
can,
later, don't worry.
yeah, have a look because I think it's quite interesting.
Thank you for taking the time for that tangent. It's been something I've been scratching my head on for quite a while, and I haven't done a deep dive myself. But I would like to know more, I think, about the aspects of cybersecurity or whatever you think is most interesting in the direction. Actually, let's go this way. What is the most interesting aspect for the development of quantum that you see as someone who's deeply in the field?
So quantum is a very big word in the sense of what there's a lot of things right now happening in the quantum world. You have quantum computing, you have quantum imaging, you have quantum cybersecurity, and somehow they're all related. Even you have quantum artificial intelligence happening as well as one of the first applications of quantum computing. It's quantum artificial intelligence, and that's very interesting because it's also heavily starting to be used artificial intelligence now. And what quantum computer will be able to do with artificial intelligence is also new things that we cannot even think of. So, for example, the optical illusions cannot be explained or discerned by classical artificial intelligence, but quantum artificial intelligence is able to understand optical illusions, for example. So we may be able to do certain things with quantum artificial intelligence that we cannot do with classical artificial intelligence, that we even do saying classical to what is currently being developed is hard to put it in a
Oh,
sense.
that's interesting. We call it essentially classical mechanics.
Yeah.
It's, in a way, right? It's the same kind of idea.
Yes, as long as it's not quantum, it's classical.
Yeah.
Even though
Wow.
it's cutting edge technology, what we're doing with artificial intelligence now. So in cybersecurity, quantum cybersecurity begins with the idea that quantum computers will be able to break the encryption that we use today. Interestingly, even more, they can potentially weaken the generation of random numbers that we use today. So that's something that not a lot of people know. I do know because I am in the field of quantum random number generators, but until I was not in this field, I was not aware of that the random number generators that we use in our computers today are very bad design in a sense. So we can still use them, but not for the next generation of cybersecurity. So basically, for example, in a Linux machine, it will see the movement of your mouse, the typing of your keys in the keyboard and things like this, and then it will mix all that in what they call an entropy box, and then it will give you random numbers out of that. And in a CPU, you may have what is called a ring oscillator, that is basically odd number of NOT gates in a ring. And when you perform measurements, you will measure either a 0 or a 1, and you can, in theory, not predict easily. And also, you cannot know if someone is manipulating the ring oscillator. So all these generation of random numbers are very slow, and therefore they're doing one thing that is called expansion of the entropy. This expansion of the entropy is using with hash functions, very similar to the ones that are used for mining cryptocurrencies, or a encryption system that we use for encrypting hard disk. That is basically, or say another AES or standards. So these are possible to attack with a quantum computer, the actual random number generation that we use today. So in order to be actually safe against quantum computers, we not only have to use post-quantum algorithms, but we need to avoid the expansion of entropy. To avoid the expansion of entropy, you need random numbers generating very fast. And one of the solutions that we have today is quantum random number generators. They use actually quantum mechanics to generate random numbers.
Well, that's the whole base. Like, for instance, electromagnetism is the basis behind the background of the current computer system, right?
Yes.
It's the same idea in quantum, except in my opinion, and I think you'd agree. I don't know if you'll agree with me, but quantum is the fundamental baseline of the universe. Meaning unless you're a huge proponent of string theory, and that's hard because we haven't verified anything related to string theory yet.
And you could not yet.
So I don't want to go down that rabbit hole because so much of that's theoretical. Well, that's all theoretical.
Oh yes, it's all theoretical, but in the quantum part, you actually can do experiments. Well, with the string theory, we cannot even dream to do experiments.
Yes. Yes, I of my own volition, I have chosen that string theory doesn't have backing to me. And I had thinking we have taken as humanity a misstep and we need to go back to the basis and start over a little bit. But that's just my opinion. And I am not the PhD in these things. So
And
go ahead.
no, string theory for me is also very much far in the future. Right now, I am more in tangible things. That's why I'm in quantums, because you can do actual experiments and you can actually verify with real world applications what we're doing in theory.
So you're familiar, and I want you, maybe this is something so that most audiences know about the double slit experiment.
Yes.
But there is another experiment that some of them know about, but there's a lot of misunderstanding around it. And this is the one I'm going to tell you about where they close the slit after the particle passes through it and impinges on the target. Do you know the experiment I'm talking about?
No.
Okay, so I'll illustrate the situation to you. There's basically, it's a double slit experiment still, except they change one of the variables. After the particle goes through the slits, they're not observing it, so it should stay as a wave. They close one of the slits before it impinges on the wall.
Okay.
And what they find is it moves back from a quantum state to a particle state and impinges as a dot.
Okay, that makes sense. Yes.
Why does that make sense if you close the slit after it's passed through it?
Because you don't know it has passed through it. How do you know it has passed through it?
See, I don't know how they figure that out. They say that they have done this correctly, and I know, right?
Let me
Go ahead.
go into try to why I think I haven't seen the experiment, so I just hypothesizing here,
Okay.
hypothesizing here.
Is
But basically, when you have a particle, we cannot think as a ball. We can only think as a sort of a cloud. And
yes.
this cloud is expanding through the universe as the particle in theory moves. So if the door is interacting with the particle, because then it's signaling the particle to be targeted and doesn't do the interference pattern, then that means that this door is interacting with this cloud, performing a measurement. So you cannot say that the particle has passed through it if there is a still interaction between the door and the particle. So the cloud has certain probability of presence in the range where the slit is and it's being closed. And then you go back to this experiment of observing from which of the two slits has passed the particle. So I guess the results that they get in that experiment is the same one as if you try to observe from which one of the two slits has passed the particle.
That
I am,
that Go ahead.
no, I am asking, is that right?
To clarify then, because so I took lower level quantum in my undergraduate work. So, but the probability distribution or the wave, it technically has an infinite distance.
Just
I did not know that.
yeah, it can expand. I mean, as long as relativity can allow you from the last time it was measured or created. So it has been created so the last time you measure was in a certain point of a space. The cloud of probability distribution can expand to almost all the directions.
I didn't. Wow. That's changed my whole thinking about the probability distribution.
Other ways, entanglement will not be possible. Or the entanglement experiments that we're doing with teleportation, for example.
Well, I feel kind of dumb not realizing that. Okay. So on that regard, though, you've heard people postulate that there's one electron doing it all. Are you familiar with that postulate that there's one electron because of, well, I've heard some people try to refute the theory because we should be able to observe positrons, more of them because they're considered an anti-electron, if I remember correctly.
Yes.
So theoretically, if we have one electron bouncing back and forth through time, we should have
Yes.
positrons. However, with what you're kind of alluding to, with the distribution technically having an infinite distance, the energy, well, it might still be conserved. You might not have an energy issue.
What I'm saying is that distance, it can be expanded wave function. It's not completely infinite. It's basically what characteristically can expand. So according to maximum speed of the electron, it can expand up to a certain distance according to relativistic physics, in a sense, because otherwise it cannot go beyond that the expansion of a wave function.
Now, you
But
mentioned,
with photons,
yes,
everything is start to be very crazy. Because for a photon, for the internal reference frames of a photon is in the whole universe in the whole time. So time doesn't pass by a
yes.
photon.
Yeah, I remember studying that. And you're telling me that, so photons aren't always visible because they're packets of energy, correct? They don't have to be on
Yes,
the visible spectrum, they're on the entire spectrum.
yes.
So that would work really well if you theoretically, like with our antennas that we were talking about, you could
Mhm.
have photons being emitted at these frequencies theoretically. And
Yes.
then in theory, when those photons hit the impinging receiver, they could transfer back to a closed or an open system.
Yeah, you could do that. Yeah.
Man, well, that explains everything within the current realm of physics. Occam's razor, if the simplest explanation is often the correct one.
Often, yes, it is.
So, and just because it's the simplest explanation doesn't mean it's easy to understand.
Definitely, it's not.
What is quantum imaging?
So,
Time, by the way,
for
we've gone over a little bit. So,
yeah, so quantum imaging is where you use entangled photons that are different wavelengths. And then, for example, you want to see through fog or smoke, you can use particles that are transparent to the fog, but your detector cannot detect those particles. So you use an entangled pair. You send one photon that is able to go through the smoke, but the other photon is a different wavelength that you're able to detect in your detector. So the detector can detect what happens in the other side of the smoke because they are entangled. So you can see through smoke that is happening on a building. There's a fire, there's a smoke, and you want to see if there is people inside or not. So you send this pair of electrons, photons, one to your detector, another to through the smoke, and then you're able to see through the smoke with your detector with different
okay.
wavelengths.
And those photons, of course, are quantized according to the specific wavelengths,
Yeah,
correct?
yes,
So, in that regard, theoretically, on a separate note, an MRI uses some principles like that. Is that accurate?
yes, it does. But in the MRI, there is no entanglement and there is no necessarily two different frequencies. In this
Okay.
case, it's using entanglement.
Okay. And an MRI, if it's emitting the photons, just for clarity, the photons, of course, are not interactive with the environment because they're not charged.
Photons are neutral, yes.
Okay. Man, there's so much to physics that I'm still having my brain break after all these years, every time. Well, I've really enjoyed discussing this with you. And if you're okay with it, I have two questions for you. Number one,
Yes.
I take this information, turn it into a newsletter. I'm going to have to expand it a lot to explain all this to the general audience. And then, of course, I'll have you review it before I ever released it. And the
Okay.
other thing, if you're okay with this interview, I'd like to, depending what you approve of, if any of it, turn it into a podcast. And then the other part is from our conversations, take shorts from it and then post those to help build publicity for the podcast and the newsletter.
Good.
This is amazing, and I hope you'll let me talk to you in the future. And if there's anything I can do for you, I would really like that. Yeah,
You
whatever.
do. Bye.
Good afternoon.